We previously introduced the definition of the derivative, which is to take the limit as h approaches 0 of f of x plus h minus f of x divided by h. As the functions that we're investigating become more complicated, this can be a very difficult limit to evaluate, and even with simpler functions, it can be a very time-consuming process. So what we want to start doing in this section is introduce properties of derivatives that will allow us to find these results faster, keeping in mind that once we find that derivative function, f prime of x, what we're constructing is a function that gives us the instantaneous rate of change of a function at any point. To start off, we'll look at establishing some properties for finding the derivative of a constant. So f of x equals a, where a is some constant, and the derivative of the function x. In example 1, we're considering the function f of x equals negative 4, and we want to find the derivative of that function. We have that graphed on this coordinate plane here. F of x equals negative 4 is just the straight line, horizontal line, passing through y equals negative 4. At a glance, hopefully we can identify that the slope of this line would be 0. And since that line continues to be horizontal in both directions without ever increasing or decreasing, that slope will remain constant. What that tells us is that at any point, no matter what x value we choose, the slope of that line will still be 0, meaning the instantaneous rate of change of that function will always be 0. And for that reason, f prime of x, the derivative of negative 4, will be 0. And that's a rule that will hold true for the derivative of any constant value. Anytime we have just a number, that derivative will always be 0 because that function has a constant slope of 0. So in example 2, when we want to find d over dx of r of x, we're finding d over dx of 2, which is again just the derivative of a constant, so that will be 0. In example 3, we want to find dg over dx for g of x equals x, which means we want to find the derivative of this function g of x. We have the line y equals x graphed over on the right. And what we can see from investigating that function is that to move from point to point, we move up 1 and to the right 1. Slope is rise over run. That means our slope in this case will be 1 over 1, or just 1. And since this is a straight line, a linear equation, the rate of change is always constant, the slope is always constant. The derivative function is giving us the instantaneous rate of change of a function at any point, and since that will always be 1 for this function, the derivative, g prime, or I can use that same notation, dg over dx will equal 1. So the derivative of a constant is always 0. The derivative of x is always 1 because both of those are straight lines and have a constant slope. Example 4 is similar to example 3, but now we want to find d over dx of t of x, where that function is 4 times x. So instead of just x, we have a coefficient in front of that variable. Whenever we take the derivative only applies to the variable portion of each term, meaning if we have a constant factor, a coefficient like we do in this case of 4, we can set that value aside and rewrite this as 4 times d over dx of x. And we know that the derivative of x is always 1. So this will be 4 times 1, or just 4. And those three rules always hold. Anytime we have the derivative of a constant, that will always be 0. Anytime we have the derivative of x, that will always be 1. And anytime we have a constant factor, a coefficient in front of a variable, we can set that value aside and just differentiate the variable portion of that expression or of that function.